Le Chatelier's principle: when a stress is applied to a system, it's going to readjust to relieve that stress. How? If something was added to a system, it's going to use up that added material as soon as possible, ASAP, by moving direction. If something was removed from a system, it's going to replace that area to compromise that was removed earlier, ASAP, by moving direction. Moving direction means that's equilibrium shift we're going to be looking at. So let's first look at the products and reactants in accordance to this equilibrium shift. So we have reactants over here, equilibrium process with the products. If there's an increase in products, so over here, how are we going to alleviate the stress over here? Well, we have to go towards the left side. Like in diffusion, for homeostasis, we want equilibrium. Where's all this craziness going to go? It's going to has to go towards the left to alleviate it. So it's going to go towards the reactant. So if we look at the next example of a decrease in product, if there's a decrease in product, how are we going to make up for this loss over here? We have to go towards the right. So it's going to go towards the product. So I'm going to be putting towards the product over here. Okay. If there is a decrease in reactant over here, so there's a decrease in reactant, how are we going to compensate and compromise for this loss in area over there? We got to go towards the left to compensate and fill it up. So we have to go towards the reactant. That's how this works. If there's an increase of pressure, there's going to be increase of chaos. There's going to be a lot of excitability, thermal energy increase. Okay, where's it going to go? In order to be alleviated, it's going to go towards fewer particle formation, so towards a smaller amount of moles. Okay, if there's a decrease in pressure, it's going to be the opposite. It's going to go towards greater particle formation. Whenever you have an increase in pressure from an inert gas, there's actually no shift at all. Okay, for a catalyst, there's also no shift at all. The difference is, for a catalyst, it gets to the equilibrium quicker. Also, for a catalyst, there is absolutely no equilibrium shift effect. Okay, I know it says may not, but for catalyst, there's 100% no effect. Okay, for inert, it really depends. It may or may not be, depending on a constant pressure or a constant volume scenario. See my 20-minute video, link is in the description for this in-depth explanation. If we look at an increase of temperature, obviously increase of temperature, you're absorbing that heat, so it's going to be endothermic reaction. If we align that with an endothermic reaction forward over here, okay, there's going to be a KQ increase. It's going to go towards the right. It's going to complete. If under this endothermic reaction we have an exothermic forward reaction, okay, so it's going to go in this direction. The KQ is going to decrease, so it's going to go in the opposite direction, to the left. Okay, if there is a decrease in temperature, obviously you're releasing energy, you're releasing heat, so this is going to be towards an exothermic reaction. If we align it with an exothermic forward reaction, it's going to be a KUQ increase. If it's going to go in the opposite realm, so it's an endothermic forward reaction under this exothermic reaction head, okay, the KQ is going to decrease. All right, so let's have a look at some examples. Take the effect of an increase in temperature. Okay, if you have increase in temperature, obviously this is exothermic because delta H is negative here. That's this over here. KQ is going to decrease, so it's going to go towards the left. How about an increase in pressure? Well, we have an increase in pressure here. It's going to go towards fewer particle formation. This has 3 moles. This only has 2 moles. Which one's less? Obviously here, so it's going to go towards the right.